This is problem 7 from section 16.8, Stokes Theorem. Done one way. In class we did it 2 ways. It took up a long time. We actually tried to do it 3 ways. One of them went astray, but it was the one I didn't prepare. So here's how to do Stokes' theorem for real. The problem is this. I have this vector field that's given, and here's my curve. It's a counterclockwise orientation curve, and it bounds a surface, a triangular region. So this is that triangular corner where everybody goes through the ones. We've seen this guy before. We know its equation, x plus y plus z equals 1, also known as z equals 1 minus x minus y. We're going to need these. The partial derivative with respect to x is -1. So we're thinking of this as g of xy. That's the book notation, but every book calls it g, every book I've ever seen. And anyway, so this guy here is a function of x and y. So we get a -1 for each partial derivative. We're going to use those later. All right, so let's give this a try. The question is this. Problem 7 says calculate this surface integral. Calculate this surface integral. Oh, sorry. The problem is this. That it's calculate. Let's get Stokes' theorem. It's up here. Here's Stokes' theorem. Right here. Stokes' theorem. The problem is the book gives us the line integral. So it's a 3-dimensional line integral. So I can't do Green's theorem. It's in 3D. So I got to have a different theorem for this. So I can either do this all the way around, which we did, and it's not on the board, but we did each piece, C1, C2, C3. We did each of those as a line integral, where we had to get the parameterization of this little line right here in that direction. Parameterization of that little line segment there. Each one came out to be a -1/3. In fact, it was really interesting. After you did the proper substitutions and simplified, we got the exact same integral all 3 times. So it's -1/3 for each piece, which adds up to -1. So we know the answer is -1. We also know the answer is -1 because it's an odd answer. It's in the back. But that's how to do it as a line integral. But it took a little while. Now let's do it as a surface integral using Stokes' theorem. So here's what you can do. I'm going to do this integral. That's the integral I'm going to do. I'm going to do it as a surface integral. Well, I have several formulas for this. One of them is Stokes' theorem, which the book says let's use Stokes' theorem on this, which means I'm going to do a curl. So I have to do the curl of big F. The curl of big F turns out to be -2x, -2z. Oh, let's get this fully on screen here. You do this curl, you get -2z, -2x, -2y. So if you remember curl, if you don't, you better look it up. That's nice. Look at that curl vector. That's not too bad. It's better than the surface integral. The surface integral, if I were to do the surface integral straight out, if I was going to do this straight out surface integral, I'd have to use x and y as my parameters, plug everything in. We tried doing it this way. We lost something. We didn't get -1. We got 3/4. We made a mistake. It's really hard to do, but do the curl first. And look how simple. That's a much simpler vector field. Let's use this problem. But here's the beauty. Here's the beauty. Ready for this beautiful moment? This is the one we're going to do. But look, that's still a vector field. This is still a surface integral. I just have a different vector field. This is P. This is Q. This is R. I have a new PQR because of the curl thing, which means I'm allowed to do this. Now there's a boatload of minus signs. You can see them all in there. Use those minus signs correctly because remember G sub x was itself a -1. G sub y was itself a -1. So I've got the minus from the formula, I've got the minus from the G sub x, and I've got the minus from -2z. Don't lose any of them. But here's what it comes out to be right here. Let's see the rest of this piece. Let's see if I can get that all on there. Went too far over. There we go. And I want just a little bit. Can I get that? Oh, I got it. Good. All right. A beautiful thing happens. Now notice this I had a 2, see this z? I had a z. I can't use z because this is going to be a dA problem. It means I'm doing dy dx. So z has to be replaced by 1 minus x minus y. Well, it's typical of this kind of problem because remember we have z equals a function of x and y. So every z can be replaced by functions of x and by a function of x and y. I've only got one z to replace. There it is. There it is. So I pop in that z, taking care of all minus signs. We end up with a beautiful thing. Negative 2x plus 2x. Negative 2y plus 2y. The only thing that survives is a negative 2. This is describing the domain. Remember, I have my triangle is tilted in space, but I'm doing dy dx, so I care about the domain of that tilted triangle, which is this baby. So that's where I get the 1 minus x from the describe the domain, this little triangle domain. So the rest is just a double integral from Calc 3, but last month. So you do this thing here. That becomes negative 2y, evaluate. I just leave that negative 2 up front, 1 minus x, integrate, evaluate, I get that negative 1. Ooh! So that we had to get negative 1 because we had done the line integral version. Each piece contributed a negative 1/3. So we had to get negative 1 and we got it. So that's how you do Stokes' theorem. And this example was not a typical Stokes' theorem problem, but not atypical either. Stokes' theorem says do that curl. Here's my thought to you. Do that curl when you get a nicer big F. If you get a worse big F, then just do the line integral. Because then if curl F is worse than regular F, do the line integral. Yeah, you got to use regular F. But if this is worse, you didn't make your situation better. But notice how this curl F is much simpler than the original vector field. So that's what it's like to do Stokes' theorem. See you later.